And now we are going to discuss about the applications of linear differential equations from the book Advanced Engineering Mathematics 5th edition by Clarence Raymond Wiley. From page 121, exercise number 11, we are given with this problem. A long slender column of uniform cross-section is built in rigidly at its base. Its upper end, which is free to move out of line, bears a vertical load F. Determine the possible deflection curves of the column and the load required to produce each one. Hint: it is convenient to take the origin at the free end of the column. Then y of 0 is equal to 0 and y prime of L is equal to 0. Now we are going to have our figure, which is this. And then let coordinates be chosen as shown in the figure. Then clearly, the moment arm of the load F about a general point P on the deflection curve of the beam is y. Hence, the equation becomes Iy double prime is equal to negative Fy. And this will be our equation number 1. Here, the minus sign indicates that y is positive. The moment is negative since it has produced a deflection curve which is convex toward the positive y-axis. And by hypothesis, or as it is given, the column is of uniform cross-section. Hence, the moment of inertia I is constant. And for equation 1, therefore it is a constant coefficient differential equation which, when written as y double prime plus f over Eiy is equal to 0, is seen to have a complete solution of y is equal to a cosine squared of f over Eix plus b sine squared of f over Eix. And this then will be our equation number 2. And to determine the constants a and b from our equation number 2, we have the information y of 0 is equal to 0 and y prime of L is equal to 0. Substituting these given equations, we get 0 is equal to a cosine squared of f over Ei, x being 0 plus b sine squared of f over Ei, and then another x is equal to 0. And thus we get a is equal to 0. Therefore, we have our equation y is equal to b sine squared of f over Eix. Then, substituting this second into condition y prime of L is equal to 0, we obtain the differentiation of y, which is b squared of f over Ei cosine squared of f over Eix. And then, substituting the second condition, which is y prime of L is equal to 0, we have 0 is equal to b squared of f over Ei cosine squared of f over Eil. And since b and square root of f over Ei are constants, the equation could be written as 0 is equal to b cosine square root of f over Eil, with b as any constant. Since cosine square root of f over Eil in general is not equal to 0, it follows that b is equal to 0. And since we have already found that a is equal to 0, it means that y is equal to 0. However, if the load f has just the right value to make square root of f over Eil is equal to n pi plus pi over 2, in which if we could substitute this to cosine will equate to 0, then the last equation will be satisfied without b being 0, and equilibrium is then possible in the deflected position, defined by y is equal to b sine 2n plus 1 pi all over 2l. And this will be your answer.